Bienvenido a un nuevo contenido de Uninorteco. No olvides suscribirte a nuestro canal.
Welcome everyone. Thank you for being here in a new session of PiA webinar series. Before introducing our guest, I want to remember you that Particles in America, PiA, is an academic initiative supported by the Asociación Argentina de Cementología, CINESTAF from Mexico, Instituto Argentino de Oceanografía, Instituto Geofísico del Perú, Mississippi State University from the United States of America, Universidad de la República from Uruguay, Universidad Federal do Espírito Santo from Brazil, Universidad de Costa Rica, Universidad del Norte from Colombia, Universidad Técnica Federico Santa María from Chile, and Sequoia Scientific Inc. from the United States. I want also remember you that in our webpage, you can find this webinar and also the past webinar. You can find all the recording as well as information related to sediment research in our continent. Today is a pleasure for us to introduce Professor Robin Davison Arnott, who is Professor Emeritus of the Department of Geography, Environment and Geomatics from University of Guelph. Professor Davison Arnott is going to talk about beach-dune interaction and the response of sandy beach and dune system to relative sea level rise. Professor Davison Arnott completed his PhD in 1975 from the Department of Geography at the University of Toronto. He was appointed assistant professor at the University of Guelph in 1976, associate professor in 1980, and currently he is emeritus professor. He has been member of different commissions and been awarded the R.G. Russell Award from the Coastal and Marine Specialty Group of the Association of American Geographers in 2000. His research interests are in coastal geomorphology, beach and near-shore processes on sandy coast, near-shore erosion of cohesive coast, coastal sand marshes, aeolian sediment transport and coastal dunes, and he has authored and co-authored many books and papers on the subject, including Introduction to Coastal Process and Geomorphology and Global Environmental Change. Professor David Arnott, welcome to this session of PiA webinar series. So now you can share your screen and go ahead. Thank you for being here.
Okay. Where is my... screen. No. Okay, I think that's it now. Let me see. Is that?
I will let you know when we see your screen. Okay.
Yeah.
Yeah.
Okay.
Yeah, you can go to the presentation. Yeah. Okay.
Okay.
We can see now.
Great. Okay, so I will be talking today about relative sea level rise and sandy beach systems. So the focus of the talk is on the impact of sea level rise on sandy beach systems, and obviously it has an impact also on some of the other things that I do work on, such as coastal cliffs and salt marshes. But today it's all about sandy coasts. And what I'm talking about here comes out of a recent paper that's right now in press by myself and Bernie Bauer on examining the controls on the response of beach dune systems to water level rise. And it's in the Journal of Great Lakes Research, and I hope some of you have been able to see it. It's in there because in the last 7 years, the water levels in the Great Lakes rose to record levels, and this triggered a lot of interest in the impact of those water level fluctuations. And what happened there has implications for what happens with sea level rise. So that's the background of why the paper is in that particular journal. Of course, the context for this is the fact that eustatic sea level rise is currently going up at about 3 millimeters per year. It may be increasing. And of course, it has impacts on all of the coastal systems, on human systems around the coast. And this has given rise to a lot of dire warnings. That is, people saying that all kinds of nasty things are going to happen. In terms of the coastal processes, one of these examples of papers that produce a dire warning is that by Vuzdukas et al. That was published in 2020 in Nature Climate Change, and it certainly got a lot of publicity. There was a response by Andrew Cooper and a whole bunch of other coastal scientists, and then a response by the authors. This is just an example of one of the many things, and we'll look at a couple of others later on. But Vuzdukas et al. Concluded that ambient trends in shoreline dynamics combined with coastal recession driven by sea level rise could result in the near extinction of almost half of the world's sandy beaches by the end of the century. So this is pretty nasty stuff, and it certainly had me wonder whether this is likely to be true or not. The paper is based on a very big study in the European Union, and it was carried out by well-known coastal scientists and engineers. And so you have to ask yourself, are they wrong? And if they are wrong, why are they wrong? So for me, the key question is this predicted loss of 50% of the sandy beaches something that we would expect, given what we understand about the dynamics of the nearshore beach and the beach fore-dune systems? So that's really what this talk is all about. What would we and should we expect it to happen to beaches and sandy beach and dune systems if sea level rise continues as it is? And of course, the latest IPCC report that came out last week is another driver of this kind of study. Okay, so when we think about sea level rise and particularly the impact of sea level rise on sandy beach systems, the Brun model is the first thing that comes to mind. First put forward by Brun in 1962, so that's a very, very long time ago. And I'm sure you all know the basic premise of the model, and that is that when sea level rises, the beach and berm area is eroded, the shoreline retreats, and that retreat continues until the amount of sediment released by that erosion leads to a rise in the bottom, the sea level bottom, in the near shore, basically. So it's quite neat because the amount of erosion is equal to the volume is equal to the height of erosion is equal to the increase in relative sea level. There's also a second part of this, and that is the Brun rule. This is the simple equation that Brun used to predict the transgression distance. That is a distance r that is shown on the top diagram that the shoreline will retreat for a given increment in sea level. This general equation essentially is the distance is equal to the slope, in this case, of the beach and nearshore, and the increment s, which is the increment in sea level. The thing is that you can use the Brun rule. It's just it's an equation that is a general format. You can use it to predict the distance of retreat without actually paying any attention to the model itself. So you can predict the distance r without worrying about whether actually the sediment eroded has raised the sea level in the nearshore by the increment of sea level rise. And that's a problem because lots of people therefore have predicted the retreat without worrying about the actual model itself. But when you come to model the response of beaches to sea level rise, to actually do some modeling of it rather than just saying it's going to retreat by this much, you then, if you're using the Brun model, you have to make sure that the amount of sediment eroded is equal to the required amount deposited in the nearshore. So Vuzdukas et al. Used Brun, and it's therefore not surprising that the beaches erode. Anybody who incorporates the Brun model into their model of the response of beaches will end up with loss of sediment from the beach and foredune system. So, okay, way back in 2005, I presented an alternate vision of this. And this, which I'm calling here the RDA model, was set up to mirror the Brun model, and that is because it assumed an equilibrium profile. So the Brun model assumes an equilibrium profile, and the RDA model assumes an equilibrium profile, but it does not have a requirement that sediment be transported offshore. Instead, it assumes that as sea level rises, the beach and the nearshore and the foredune all rise synchronously with sea level rise. And so the outcome of that is that the sandy beach systems are preserved. The dune remains intact, the beach remains intact, and the nearshore sediments all migrate landward. And so for humans living along the coast, this makes a big difference. And so one of the questions then is, well, is the RDA model the right one as compared to Brun? And if so, is there any evidence that might support it? So the paper that Bernie Bauer and I produced essentially attempted to verify, to update the RDA model and to provide verification that this synchronous migration of the nearshore, the beach, and the foredune can and does occur. So this is the objective of the paper, and I, at the end of it, part of what I want to show is that it can be, the new model can be used to guide the development of predictive models of sandy coast evolution. Okay, so sorry, let me just get rid of this. Yeah, so the key part of the revised RDA model, the RDA 2021 model, is that we replace the equilibrium profile with one in which we assume dynamic equilibrium in each of the three profile components. That is the upper shore face or near shore, the beach, and the foredune. And this model also allows for small net transfers into the system, so we can have sediment coming into the system from the lower shore face, and we can also have sediment leaving this part of the system into the dune field or back barrier. The only thing is that the assumption is that these net transfers are relatively small compared to the amount of movement or transfers within that fore-dune beach and upper shore face. So that's a major change to the assumptions of the model. So we assume then these three primary zones, the shore face, upper shore face, beach, and fore-dune, and that they're in a state of dynamic equilibrium. And we assume that, as I said, the sediment transfer rates within and between the primary zones are much greater than into and out of it. So one of the we also assume that the biophysical controls, things like wave climate, wind and wave climate, and say the vegetation of the fore-dune. But a key one here is that the relative sea level rise rate is less than 10 millimeters per year. And one of the things we found from the work in the Great Lakes is that when you get a sea level rise rate that's much greater than that, then the ability of the sediment in these three primary zones to migrate is reduced. We also have a time scale that's a decadal to a century, and that's because as you get towards a century time span, we have to allow for evolution of the coast, and as the coast evolves, it then changes what's happening in terms of sediment movements, both onshore, offshore, and alongshore, and so those become more difficult. Okay, so I'll just go through here fairly quickly a couple of the look at what's happening first of all between the beach and the nearshore in terms of this dynamic equilibrium, and then move from there to say something about beach dune interaction, because Brund says nothing about beach dune interaction, and I think a key to understanding the evolution of sandy beach and dune systems under sea level rise is to understand what's happening with the beach dune interaction part. So we'll come to that in a minute, but let's just look first at nearshore beach interaction. And one of the first sort of conceptual models that was produced in terms of this goes back to the work of Shepard on the west coast of the United States. So in 1950, he produced this sort of model in which you have a barred coast during the winter or the storm season with no boom and bars in the nearshore. And then during and this is produced because of storm wave action. And then in the summer period or the fair weather period, the long period swell waves would move sediment onshore, build a big boom, and the bars would disappear. And so on an annual basis, the profile oscillated between these two end member states. So we can go from that to say that, in fact, as we start looking at sandy beach systems in different parts of the world, then we can have other combinations. So, for example, in the Caribbean, where I grew up and where I've done a bit of work, coasts are never barred. And this would be true also for the Caribbean coast of Colombia, for example. But we can still put forward a model of how the beach and nearshore systems respond to storm events and to swell wave events and so on. Okay, a lot of this has been now seen as more complex. Wright and Short in Australia developed the beach state models, and these have been applied to a whole range of different coasts, including the southwest coast of France, where Castel and his group have done a lot of work on this. And so what these all show is that the nearshore and beach systems, we have sediment transfers between them, but they're essentially in a state of dynamic equilibrium, which is described by parts of the Wright and Short model. One example of this is comes from work that's been done in the United Kingdom or Great Britain and in the west coast of Europe, because in the period 2013-14, there were that whole area, that whole coast was the subject of extreme storm activity, and so there was lots of erosion of beaches and of dunes. And what we're seeing here is an example from Truqueville, which is where Castel and I work on the southwest coast of France. And the gray line here shows the beach volume. The dark black line here shows the beach volume. And between the start and end of that winter, there was tremendous erosion of both the beach and the foredune. But what a paper by Daudet et al. Showed was that if we continue to monitor the beach over the next few years, the beach recovers. So that within 3 or 4 years, most of the beaches in this region had recovered to pretty well their previous, the volume previous to the storm events. And while the dunes had not recovered as much, in most areas the dunes were recovering. In fact, there's another recent paper by Constantinou looking at beaches in the southwest of England. And what we see from there is that basically all the beaches and pretty well all the dunes have now recovered to their state as they were before this big storm season occurred. So it gives a fair amount of support to the idea that the beach and dune systems are in equilibrium, and that even with very large storm events, the sediment is just stored in the near shore and makes its way back onshore. So the summary then suggests then that where the water level fluctuations, the water level fluctuations and the changes in beach and nearshore morphology are much greater than the impact would be from a few millimeters of increase due to sea level rise over a period of a few years to maybe a decade. So that I think supports the idea of the RDA model that as long as the sea level rise is small, this dynamic equilibrium in the nearshore and beach will allow that whole lot to shift synchronously with sea level rise. So then this brings us to the other really important component that we're interested in, and that's what's happening to the sediments that are on the beach and in the dune. And so that the exchange of sediments between the beach and the dune, or beach-dune interaction, involves the interaction between two major forces. As we go offshore, we get into processes of sand transport that are driven primarily by water, by the wave action and currents in the nearshore. On the beach, we oscillate between water and wind because the beach is sometimes exposed and sometimes covered by waves. And so during the fair weather periods, wind can transport sand on the beach, and during the storm events, it doesn't. And then as we get into the foredune, then the sand transport there is dominantly by wind, obviously. And this is a picture of beach system at Greenwich Dunes in Prince Edward Island, which is in the Gulf of St. Lawrence, where for the last 10 or 15 years, we've done most of the work on beach dune interaction. So we'll see a little bit more of that in a moment. So we're looking at interaction between the beach and foredunes, and of course, foredunes are not included in the Brun model, but the RDA model assumes that we're dealing with a sandy coast backed by some kind of vegetated foredune. It probably does work also with dunes in more arid regions where you may have NEBCA, but I've not studied that in detail yet. Okay, so the details of that beach-dune interaction will vary with controls such as the tides, the wind climate, the wave climate, and so on. And they will vary also with the vegetation type and density. So you've got an example on the left from South Australia and another one on the right from the Caribbean, from St. Kitts. Two different sets of vegetation types, and the way in which the foredune develops will differ, but the processes are essentially the same. Okay, so what we can look at in terms of beach-dune interaction is erosion of the foredune by wave action during storms, the recovery of the beach, and then the growth of the foredune. So the star slope, that is the slope facing the sea, is eroded and scarped or cliffed during storms, and that takes place in a matter of a few hours to a day or two. The slumping of the cliff of the dune initiates the buildup of the dune ramp, and we can see here there are bits here that resulted from the slumping of material from the dune, and the lighter material here is probably dry sand that's been blown onto it. This ramp is really important because where there's a cliff face in the dune, it acts as to retard sediment transport directly from the beach onto the foredune. But where that has built up to the level of that top of that cliff, then sand can go all the way from the beach up and eventually over the dune. So the rebuilding of the beach, followed by rebuilding of the of this scarp of this ramp, allows connection of sediment between transport by aeolian processes from the beach and over the dune. So a key thing to the the ability of the foredune to migrate, to transgress landwards, is what happens during these major storm events that produce this erosion and cliffing of the foredune. So here's a cliff dune in 2011, resulting from two major storms in the winter of 2010-2011. So you can see that the dune face is nearly vertical here, and that it has produced slumping of material from the top, held in place by the vegetation. The photograph over here on the right is from Denmark, from the Jutland Peninsula in Denmark, and this is just 2 days after a major storm event. So what was a big boom here has now been removed completely. The dune, the beach is sloping. That's the storm slope. The cliff, the dune has been cliffed, and this point here, all the way along, marks the limit of the erosion by wave action. And so if we take that point, that's an important point marking the trajectory of how this beach is going to progress. So if we have a storm of this same magnitude, say 10 years from now, when there's been several centimeters of sea level rise, then the water level would be at this elevation rather than at this elevation. And so that would produce erosion and cliffing and retreat of the cliff some distance inland, maybe a meter further. So if we mark this point as where the dune is eroded after a storm of this magnitude, if we then translate that storm every 10 years, then that will mark a series of points that transgress landward along the slope of this storm beach. So this is the key slope that marks out the trajectory and allows us to predict the retreat distance of the foredune. Okay, I want to give you some examples from the work we've done in Prince Edward Island on beaches and dunes, because much of this paper and the work on the conceptual model, that update to the conceptual model, comes from the work we've done here. We started in 2002. We did our last experiment in 2010, and we continued monitoring these places until 2016. So about 14 years. And so a lot of the insights come from this. One of the key things that I want to point out is this is about 4 or 5 kilometers along here. Sediment transport is from left to right here, east to west. And there's another profile out here, but we have profiles along here. And in this section, in Reach 1, the littoral sediment budget is negative. And so even if we kept sea level exactly the same, this portion would be retreating because the budget is negative. As we get here, there is a reduction in the rate of sediment transfer, and we go from negative to neutral to positive in this direction. And so profiles around here, 5 and 6, are slightly negative, 7 and 8 are neutral, and out here, 9, it's positive. This is in part what we will be able to show you is how the sediment budget makes a difference to the response of the profile to relative sea level rise. Okay, so let's give some examples from our work here. This is the picture of the dune. This is taken from a camera system mounted on a mast above the dune. And this is in June of 2011 after 2 big storms that I showed you. The beach is flat, there's no berm, the dune has been cliffed, and there's a very steep slope with something here. If you look at the same site, same picture from the same site in 2016, what we'll see is that there has been recovery. There's been a big berm produced that has been colonized by, in this case, marram grass. So we have an embryo dune system formed. Sediment has been transported from the beach across this and up the cliff. So we now have a ramp that has become vegetated too. And in the first couple of years before that happened, the cliff edge that we saw here was eroded by wind action and sand transported over here. So this marks the retreat of that cliff, the top of the cliff, before we have vegetation here. We carried out a whole series of experiments to measure sand transport by wind on the beach and across the dune. The first experiment was in 2002 and the last one in 2010. And this shows just some of the equipment that we use to monitor the winds. So we use 3D sonic anemometers, 2D sonic anemometers. In this case, we were using sapphires to measure sand transport, as well as small vertical sand traps. In this case here, we're using similar arrangements of 2 and 3D anemometers, cup anemometers, and we're using here also Wengler laser sediment detectors to measure the sand transport, and we also used sediment traps. So we've been able to measure what the controls are and what the relationship is between the winds, the wind speed and direction, moisture content on the beach, vegetation cover, and transport over the foredune. And that's all summarized in a paper that is there in Earth Science Reviews in 2017. So those data give us some insights into the actual processes. And this comes from a paper, Allahead et al. In 2013, and it shows the results of measurements we made on an annual basis at each of those profiles that I showed you earlier. We don't need to worry about the details, but what it shows is the amount of sediment deposition in terms of centimeters increase in the height of the dune each year between 2002 and 2009. There isn't sediment recorded in each year, but in most years there is. And as we go from line 5 to line 6 to line 7 and 8, we see that there is always deposition. So there's always sediment transport over the crest and onto the lee slope and out to the base of the lee slope. So each one of these has sediment going right over the foredune, if you look at it like that, and right to the base of the lee slope, and in fact, some sediment going beyond the lee slope. So this shows us that migration of the foredune can occur simply by sediment transfers up the star slope, over the crest, down to the lee slope, and beyond. Let's look at what happens in terms of the actual profiles. So we have annual profiles, or in fact, sometimes more often, but annual profiles. And I've just selected some of these to show the change in those profiles between 2002 and 2016. So line 5 is the one where we still have a negative littoral sediment budget. So the red profile is 2002. The black profile is 2016, so that's 14 years of change. You can see here that because the budget is negative, the whole system is migrating landward. And so this means that the toe of the foredune migrates landward, and the crest of the foredune also migrates landward. In this case, it migrates about 8 meters, maybe 8 to 10 meters over that time period. So close to a meter a year. But notice that it's also slightly higher in elevation. So if there has been an increase, and there is a small increase in sea level, that is maybe reflected in an increase in the height. As we go towards line 6, the budget becomes less negative, and so we can see here a small retreat of the toe of the foredune, and a small retreat, just a couple of meters, of the crest. But similar to the line 5, we can see that the lee slope is increasing there is always an increase in the elevation of the lee slope, and so sediment is coming over the foredune and being deposited, in this case, more than 30 meters landward of the crest. Finally, if we come to line 8, here we're in a section where the littoral sediment budget is neutral. So the amount of sediment coming into the beach in this area is equal to the amount of sediment that's going into the foredune or along shore. So the beach sediment budget is neutral. And we can see here that there is no change in the position or elevation of the base of the star slope. There is, however, a small increase and continuing increase, in this case, about 2 meters increase in the height of the foredune, and a small amount of increase in the lee slope. So although the littoral sediment budget is neutral, in fact, in this case, the dune sediment, the dune is able to increase in volume. So a key thing that I want to point out from this is that we cannot understand what impact the rise in sea level will have on sandy beach and dune systems without taking into account the littoral sediment budget itself. And that in many cases, I'm going to say this now and we'll come back to it, the kind of crisis that people evoke for retreating coastlines is mostly due to a negative littoral sediment budget, which would result in a retreat of the coastline, irrespective of what's happening to the sea level. So the purpose of the RDA model and the revisions to it is in part to allow us to separate out what kind of things we can expect that are due solely to sea level rise from that would happen as a result of a negative sediment budget and coastal evolution over centuries. Okay, so what comes out of the work we've done is that, similar to what we saw for the nearshore and beach, the beach-dune interaction produces, or as a result, it reflects a dynamic equilibrium within the beach and the foredune. And the changes that we see in the beach and the foredune are, again, a much greater magnitude than any small change due to relative sea level rise. As a result of that, then, we can expect that the kind of transgression that I've said will occur, and that the foredune will shift synchronously with a rise in sea level. This, of course, is all assuming that sea level rise is less than 10 millimeters per annum. Okay. So in the same way that you had a Brun model and a Brun rule, you can produce an equivalent to the Brun rule, which we've termed Robin's rule. It wasn't me who suggested it. That was Bernie Bauer who suggested it, but it's Robin's rule sounds good to me. So Robin's rule, the equation that we use to predict R, which is the distance of transgression over the time period we're interested in, is similar in its formulation as the Brun rule. You can produce a whole series of them. The key components, again, are so that the actual regression distance or recession distance is a function of the time period that we're interested in, the slope, and the increase in sea level. But a key difference here is that this slope is not something that goes from the boom crest to the seaward limit of the nearshore. The slope that we're interested in is the slope of the beach profile after a major storm. In other words, the storm profile. So it's the average storm beach profile slope. That's often a little steeper than the slope that would come out for Brun rule. But the key thing is, it's not reliant. We don't have to worry about what's happening in the nearshore. In the Brun rule, you have to, in order to get that slope, you've got to measure the nearshore profile, and you've got to determine where that limit is, that border between the seaward end of the nearshore or upper shore face and the lower shore face. We don't have to do that here. In fact, the retreat of the beach and foredune is independent of the changes that are taking place in the nearshore, or any changes that take place in the nearshore. If we use the Robin's rule, then we can look at a couple of examples of the retreat rate that would be predicted. So if we assume a sea level rise of 0.003 meters per year, that is 30 centimeters a century, and we do that for 100 years, so one century, then if the storm beach slope is 1 to 15, the shoreline would retreat a distance of 4.5 meters in those 100 years. If we have a more gentle slope, storm beach slope, with the same increase in sea level, then the retreat distance would be, recession distance would be 12 meters. So those are not very big numbers. And if we're looking at, these are the current rates of sea level rise, so then we can predict, assuming these rates stay the same, that for most sandy beach systems, the retreat rate will be 12 meters or less. That's what Robin's rule predicts. And that's only for the sea level rise component. If we assume that that sea level rise increases to, say, 5 millimeters a year or 50 centimeters a century, those numbers rise to 7.5 and 20 meters. It's still quite small distances, and still very small compared to the recession rates that we can get with only modest negative littoral sediment budgets. So I think this is a kind of number that I want people to look at in assessing what may be causing shoreline retreat and comparing it to what might be predicted from a negative littoral sediment budget. Okay, all right. So I want to give an example here of, there's a lot of information in the paper with myself and Bernie Bauer on the stratigraphic evidence for translation of sand and gravel, in fact, with rising sea level. I want to take a look at what's happening in the Gulf of St. Lawrence because it's an interesting site. And we look in particular at these areas here, and I'll bring this up for a second. We're going to look at these, the red lines mark barrier systems that have been relatively well studied. And the key thing here is these are barrier systems that exist in an area where sea level has been rising for 6,000 years. And I'll come back to that in a minute. So here's the sea level rise. This is on Prince Edward Island where we've been working. This is the tide gauge for one of the harbors there, and it shows an increase, a linear increase of about 3.2 millimeters a year. This is only from 1911 to 1998. But Don Forbes and his group have put together a curve for the last 6,000 years based on a whole range of different sets of evidence that shows if we go back 6,000 years and look at the average rate of change in sea level, it's also about 0.3 meters per century for 6,000 years. This is a function of, I'm not sure if I've got it here. No, let me go back. This is a function of isostatic depression, and so it's the collapse of the forebulge when we had when there was ice present in the region, and then of the impact of sea level rise on the continental shelf of Canada, which is also causing a certain amount of depression. So where's all this sediment going? So for 6,000 years, sea level has been rising. And if we look at the coasts of New Brunswick and Prince Edward Island, we see they are characterized by these barrier systems that look just like barrier systems in many parts of the world. There's continuous barriers. They are backed by lagoons and estuaries. We can see in places they are overwash, so sand is being transferred through overwash. We can see in places there are inlets, and so sand is transported in through here. And there are sand dunes all along here, and it's the same with these. Again, overwash in areas, continuous dunes in other areas, inlets going into lagoons and estuaries. And it's probably looked exactly the same for 6,000 years, except that it was 2 or 3 kilometers offshore when it began. Okay. So what's happening? Where is all this sand going? Well, if we look offshore, this is a large section of the northwest shore of Prince Edward Island. And what's happening here is that this is from side-scan sonar mapping. All this area out here offshore, some up to about 7 or 8 kilometers offshore now, is primarily bedrock, exposed bedrock, or bedrock covered by a thin veneer of sand. So this is essentially a ravinement surface produced by material, sediments deposited on here being carried landward, and they now form the barrier systems and beaches that extend all the way along this area. So the barriers I showed you were here, and the area that we're working in is in this section here. So what's happening is that as sea level rises, the wave action reworks sediments that are there present on the shelf and on the beach and below the beach. And as the transgression takes place, the sediments in the upper shore face or near shore move landward with the beach and dune system, and they leave behind this ravinement or erosional surface. This is true in the Gulf of St. Lawrence. It's true on much of the east coast of the US. It's true in Australia. It's true in the Bay of Bengal, where we've done a little bit of work. And so there's lots of evidence for this. And so sediment doesn't go offshore as the Brunn rule would suggest. In fact, it migrates onshore. And here's just some pictures showing some of that. So here is a barrier overwash. This is in Prince Edward Island. These are all from Prince Edward Island. So there's areas of overwash in between small areas of sand dune. There are tidal deltas, ebb and flood tidal deltas, moving sand into the lagoons and into the estuaries. On the dune systems, there are blowouts happening, and those blowouts move more sand inland to aid the transgression. And then there is simply sediment transported from the beach over the foredune and into the back barrier area. So all these processes are helping to move sediment from the nearshore and beach landward as the transgression takes place. Okay, well, let me wrap this up by saying a little bit about some of the complexities of the model. If we look at a longer time scale, then we allow for a certain amount of sediment transport from the lower shore face into the upper shore face, and sediment moving from the foredune into the back shore. Some of what happens depends on complexities such as what's happening in the upper shore face. If that shore face has lots of sediment, then that sediment is moved inland, it migrates with the lower foreshore, and as we see, it can leave behind a ravinement surface. If, however, bedrock is very close to the surface, then there's very limited supply of sediment here, and so much less goes into the nearshore as it retreats, and this leaves behind a surface that is the bedrock that we saw in Prince Edward Island. Other set of complexities depend on what's happening on the land part of it here. So obviously, in a large part of the world now, the beaches can't migrate freely. So the foredune can't migrate because there's urban infrastructure and a whole bunch of other human activities going on here. And so this just ends. And that coastal squeeze, as it's called, is a much bigger threat to human activities than is the actual process of sea level rise. If the slope is roughly the same as the nearshore or the storm beach profile, then the whole thing migrates landward as Robbins, the RDA model would predict. And if we have if the landward margin is much steeper than that, and that may be a dune field, for example, or it could be cliffs, or just fairly steeply sloping land, then the rate of retreat obviously will be much smaller, and the volume that's needed will be positive. That is, there'll be more sediment or material there than is needed. It becomes a little more difficult when we have a negative sediment volume, and this occurs where we have a flat or a slope that is sloping downward, as you often get on a barrier island system. And so this produces a negative volume, which means that the migrating foredune has to build some of that as it transgresses. And we see an example of this here. So let's see, this beach surface is, the landward surface is nearly horizontal. As sea level rises and as this dune transgresses, some of the sediment in the dune has to build up a base for the rest of the dune. And that results in a gradual decrease in the height of the dune if there's no extra supply coming in. And in this case here, we see that with sea level rise, we begin to get a lagoon and marsh system present. So this landward marsh is a complexity that happens as the shoreline evolves. And it's not accounted for in the RDA model. What it is a complexity that anybody who's doing coastal management will have to take into account. I'll end here with this. We've just been talking a little bit about accommodation space, and this is essentially the space that's available for deposition of sediments. And usually we think of the accommodation space as being drift or downstream of whatever the transport system is. So the back barrier marsh or lagoon is an accommodation space for transgressing barrier. But it's important to note first that you don't have to fill the whole accommodation space necessarily, but more important that we have to define the direction of net sediment transport. And if the direction of sediment transport is in the opposite direction, then the space won't be filled. So here's another example of a catastrophic beach sand loss. And this is a paper that came out just a few weeks ago by Peterson. And what it does is it suggests that there will be catastrophic beach sand losses on the Pacific Northwest coast of the USA because there is accommodation space in the nearshore submarine area. And they're expecting then that sea level rise will result in transport offshore based on the Brun model to fill that accommodation space. If you look at the RDA model instead, what I would suggest is that the sediment will migrate landward as cliff erosion and estuaries migrate, and that there will be no sand loss or limited sand loss offshore to the accommodation offshore because net sediment movement is always in the onshore direction. Okay, and I'll end, with a couple of implications for numerical modeling. So if we look at the subaqueous realm, we've got models such as Delft 3D and XBeach, and they apply to sand transport in those zones. We've got some recent models of aeolian sediment transport that have been developed for beaches and foredunes, Hunout and De Vries and Van Rijn and Stripstein among them. And even now a model by Cohn et al. That kind of pulls together three standalone modules to model the subaqueous, the subaerial, and what happens in vegetation. But if we're going to apply these models, these are basically short-term models. And if we're going to apply them to forecasting the response of beaches to decades and century, we need to have a reduced complexity models. And some of you may be aware then of two recent models, one by Hallin et al. And another by McCarroll et al., that attempt to explore the effects of relative sea level rise on a decadal scale. And I have to tell you that McCarroll and his group and Hallin and her group are really good scientists and have done really good stuff. So I'm picking on their models because they happen to use the Brun model to calculate sediment transfers. And so within their models, anytime there is sediment transport, it transfers sediment to the the nearshore in a volume that's determined by the Brunt model. And so naturally, if we look at the impact of these models, they all predict not only transgression of the shoreline, but they produce loss of sediment. And if you were to do these models, but assume that sediment was transferred synchronously with the rise in sea level, then the losses of sediment that are predicted by these models wouldn't occur. Okay, so here's my take-home message. We can expect that many sandy dune and beach systems will translate synchronously with sea level rise, and the systems will not be altered substantially unless there are other major controls in play, other major controlling things such as a negative sediment budget. And this occurs because the rates of morphodynamic adjustment are an order of magnitude greater than the inundation potential. But we're dealing with a complex environment. And again, I say one of the lessons from the Great Lakes environment is that if your sea level rise is really quick, then the processes that lead to transgression, synchronous transgression, may not work to the same extent that my model envisages. And the last bit is basically, we should always look at the assumptions that underlie any predictive model. First of all, if we're going to use it. And secondly, if we're appraising publications that make use of them. And so when I say things about Hallen and McCarroll and so on, it's because I look at the assumptions they make and I don't agree with, or I don't think that those assumptions are correct. So, and of course, if you're going to look at the assumptions of predictive models, they also apply to the RDA model and to Robin's rule. So you have to subject what I've just said in the last hour to the same kind of scrutiny that I would ask you to subject all the other models to. Thank you. Okay, let me escape from that and I guess actually I can. Right.
Thank you very much, Professor Davidson, for this great talk, fascinating ideas and concept. So at this moment, we have time for questions. So the first questions come from Jairo Cueto. Jairo is asking, the RDA model seems to work well for natural beaches with little human intervention, but it is accurate for highly populated beach areas where dunes are inexistent and wind transport is very limited.
Thank you, Jairo, for the question. Yes, some of the to the extent that the processes that form part of the model work, there will be some predictive ability from the RDA model. But as I think I said, and I made clear, is that with the model begins with the assumption that we're dealing with a natural beach and dune system, and the more you change that or alter those natural, the natural functioning of the beach and of the foredune, the more you will take away from the ability of the model to work. So we have many beaches here in the Great Lakes and on our east and west coast where the model just can't work because human intervention is too great, and others where it works to a limited extent because the interventions are fairly small. And if you look at small amounts of, say, beach nourishment or beach use, modification of dunes because of heavy traffic there, the model still works fairly well.
Thanks, Professor. There is another question from Francisco Pedocchi. Francisco is asking, thank you for your presentation. Do you have any comments on the role of vegetation on the Dune beach dynamic?
Yeah, we say a little bit about this in the paper that we did, but I think the vegetation is really a very important part of the dynamics of it. And of course, one of the key roles is to produce the foredune and to reduce the rate of sediment transfers across the dune. So the vegetation, from that perspective, acts as a regulator, and it has that effect in terms of the amount of sediment that it stores. It also has a very important role because it does limit very critically the amount of erosion that takes place during a storm event. And those pictures that I showed of, say, for the storm both in Prince Edward Island at our study site there, and in Denmark, that the storm event in Denmark was something that had I think a 3-meter storm surge and waves that are about 6 meters high offshore. And yet most of the toe of the dune only retreated about 5 meters or less in that case. And that's entirely because of the binding effect of the vegetation. That marram, in both cases, marram and alignments, were really important in providing strength to the sediments. And there are quite a few papers now that have been trying to determine exactly how effective different types of vegetation are in doing so. I think, in fact, we'll see that there are differences between different plant types and how much protection they afford. But in fact, I think those differences are quite small compared to the difference between having any vegetation and no vegetation at all. And we see this, I think, because some of the early tests, wave tank tests, were trying to apply I think the X-beach to beaches and dune systems were done using just a pile of sand at the beyond the beach in a wave tank, and the recession rates when you put any kind of wave action on them were so quick that what they did to simulate that is to say, well, we know it doesn't go back that fast, so we'll put in a coefficient that reduces the amount of recession during a storm by, say, 10 times, or reduce it to 1/10 of what it would be. So the vegetation is really important for both protecting and reducing the amount of erosion during a storm, but also, obviously, of course, for storing that volume of sediment. And so it plays a really important role in that dynamic balance between storm erosion and then taking sediment to the beach on the near shore, and then trapping that sand when it comes back ashore.
Okay, Professor. This comes from Gerardo Perillo. Many thanks, Robin, for a very good talk. Even though you comment the effect of beach volume, small when you have a rock outcrop near or at the surface, there is still the effect of the rocks themselves in reducing the inland translation. What do you think about this issue?
Yes, I mean, again, the assumption that is made in the model and in most, it's true of Brun as well, is that we're dealing for the RDA model is that the beach and foredune are in sand only. It doesn't. The RDA model will operate if there is bedrock offshore, as long as there's some sand in the near shore. And in fact, in Prince Edward Island and much of the Gulf of St. Lawrence, that bedrock outcrops in the near shore. It outcrops in water depths of 4 to 6 or 7 meters. And so the seaward edge of the nearshore is in fact in bedrock, but it doesn't affect the operation of the model because the model is independent in a sense of that. As long as there is a sufficiently wide inner nearshore to allow sand to transport back and forth between the nearshore and the beach, that's fine. If you have sand, if the dunes lie on top of bedrock, and that is so that we have some of this in places in Prince Edward Island, the bedrock is very close to the surface, then yes, that will reduce the rate of transgression, especially if the transgression is occurring due to a negative littoral sediment budget. I'm not sure what it does in terms of retreat of the dune, but generally speaking, as the bedrock gets closer to the surface, or in fact, if you have a dune that's maybe perched a meter or two above the bedrock, and so the bedrock is intermittently covered with sand, then obviously it will reduce the rate of inland migration. Yeah.
Okay, Professor, thanks. I have one question from my...
Sorry, could I just, one other thing?
Yeah, of course.
These are complexities, and I know that there are many beaches with these kinds of complexities, and so we do have to always take those complexities into account. Okay.
Okay, Professor, thanks. I have one question from my own. You mentioned that we are not really in a net scenario of retreating, but in a scenario of geomorphological adjustment, right? And such adjustment is highly related to the beach and dune system. What happened with that system when in which there is no dune system? Because you presented a figure, a very generous figure, in which you located the infrastructure behind the dune. But you know that in some places in the Caribbean, and especially in Colombia, we used to remove the dune to be closer to the water in order to build houses, hotel, and touristic infrastructure. What will happen in these beaches?
Well, I know. Well, what will happen in those beaches is that if sea level is rising, you really, in the end, have two choices. You can armor the whole beach, which of course people do, and that then takes away from the. And I've seen it in Colombia. I've seen it in many islands in the Caribbean. It removes the kind of thing that people come to the beach for. And of course, obviously, in the end, it's very expensive to do that. Or you can do as, say, Woes Lucas and I'll suggest, and that is you can take the Dutch approach, and that is you just bring in as much beach nourishment as you can. And so the Dutch do that. You know, and I've had, as a result of this and some earlier work, lots of discussions with some of the Dutch coastal engineers about this. I mean, the Dutch they have no choice, because if the walls break in Holland, everything gets flooded to a depth of, you know, tens of meters. But for most places in the world, there's just not enough sediment offshore to provide that kind of thing. So the answer is surely to remove the and certainly in what we advocate in much of Canada, not always successfully, is to move people back, and so ideally you have the houses move synchronously with the moving beach. That allows you to have a continuous beach for people to enjoy all the time, but their house has to be further and further back. So the house that your grandfather built goes, and you have to build a new house further inland, and that to me is a simple way. It's not always easy to persuade people to adopt that, as I'm sure you find.
Yeah, of course. So if you don't replace the dune system, the nourishment process will be
you have to just keep nourishing the beach, and that just goes.
All
Yeah.
life.
And of course, it's in England, in the United Kingdom, we have been looking at. They have taken some of the sort of modeling from the Dutch and others in the European Union, and they believe that we should open up the foredunes to inland transport of sand so that we can protect certain species of plant or beetle or lizard that like open sandy environments. And they encourage people to run all over the dunes so that we now no longer have in many of their dunes, there's no embryo or incipient dune system anymore because they have destroyed all the vegetation, and the vegetation on the foredune is destroyed. So instead of the volume of sand coming off the beach being trapped close to the beach, it's now going way inland. And so one of the things that we see is that means that the dune system is migrating inland because there's no vegetation to hold it in place. And so in Sweden, they've actually measured the impact of this. And it shows us that, a vegetated dune is a good thing. But let me also say, I've been to places, say, for example, the coast of Namibia, which is an arid coast, and it has just Nebka and no real foredune. It doesn't matter. The sand moves inland, but it is trapped in a much wider zone, and there's no big dunes there. The model will still work in those circumstances.
Okay, Professor. This is from Flavia Lins de Barros. Thank you very much for the presentation. I would like to know if it's possible to incorporate the vegetation on Robin's rule. So difficult.
Yes, it is. Robin's rule is a conceptual, you can't do it into Robin's rule because it's, in a sense, it makes the assumption that the vegetation is present. If you are producing, but Robin's, that's simply an outcome of a conceptual model. And the RDA model is also a conceptual model. And so somebody else has to go and do the modeling, the sort of thing that Hallin and others have been doing. I'm not going to produce those models. I'm not going to try to modify X Beach and the Hohenhout and De Vries model and put them all together. I'm too old for that now. I'm retired and I don't have to do it. But somebody else does, and there's lots of opportunity for doing that. And I think it is necessary to include vegetation in your model in the way that that others have tried to do, and you can do it fairly superficial level, or you can try to incorporate dynamic modeling, which would see feedback between erosion and dune vegetation growth and so on. That's really tough to do well, but that's a challenge for somebody else, not for me.
Well, Professor, I want to thank you again for your presentation, for your time and explanation about this topic. And for all the attendants, thank you very much for being with us. Keep in touch. Please aware for the next month. We will have a special session because our first year of broadcasting. So we will be expecting you. So thank you very much, and see you next. Professor, see you.
Can I just say, I'm happy to, if anybody has any other questions, just email me directly and I'll be happy to answer them. We're still slightly in pandemic mode, so I'm not going anywhere.
Yeah. Okay. Thank you. Bye-bye.
Thank you for having me. Bye-bye.
Los siguientes contenidos de Uninorteco te pueden interesar.